Recall from Functions 1 that we use graphs as visual representations of functions. For this lesson, I will start by describing graph transformations generally, and then we'll use an example to make it clearer. First, I'm going to draw the graph of some function f of x by making the statement y is equal to f of x. We don't need to know the function itself, we just know that its graph looks like this. Now I emphasize the point from Functions 1 that for any point along this curve, if you input the x-coordinate into the function f, the output you get is the y-coordinate. When we transform a graph, what we draw is no longer y is equal to f of x, but different variations of f of x, which I will now show. The first variation I will show is when we draw y is equal to f of x plus a. We are now saying that at a given x, the y-coordinate is x inputted into the function f, as before, but with an added extra a. This means the y-coordinate is what it was before, but a more, so we shift it upwards by a. In other words, we have translated the graph by a in the y direction. The next variation is if we draw y is equal to a times fx. In the same way as before, we see that now the graph would look like it did originally, but at every x-coordinate, the y-coordinate would be a times greater. When we draw this, we see that it has the effect of stretching the graph a times in the y direction. Now we look at the variation of y is equal to f x plus a, this time with the plus a in the bracket. This one is a bit harder to understand. To work out the y-coordinate of a given x-coordinate, instead of inputting that x-coordinate as the argument to the function, we instead input the value that is a greater than x. So every point of this new graph copies the point that is a ahead of it on the x-axis in the original graph. When we draw this for every point, we see that it has the effect of shifting the graph to the left by a. In other words, it is translated by minus a in the x direction. Finally, we see the variation y is equal to f with argument ax. We realize in the same way as before that at each x-coordinate, we are using the y-coordinate of the point that is a times x in the original graph. When we plot this, we see it has the effect of squishing the graph by a factor of a along the x direction. Instead of saying squished by a factor of a, we might say stretched by a factor of 1 over a, which means the same thing. Now we do all this with an actual function, y is equal to f of x, which is equal to 4x cubed. We are told to write the expressions for and sketch the following 4 functions. To help us write the expressions, we choose to write the function without an argument. For question 1, we fill x into the argument of f, write it down, and then put a minus 3 on the end. Drawing it, we know we translate it by minus 3 in the y direction. For question 2, we write out the expression fx and multiply the whole thing by 3 to get 12x cubed. To sketch it, we stretch it by a factor 3 in the y direction. Question 3, we fill x plus 2 into the argument for f, and so we get 4 brackets x plus 2 cubed. To sketch it, we translate the original by minus 2 along the x-axis. For question 4, we put 2x into the argument of f, which we can write as 32x cubed. To sketch it, we stretch the original by a factor of half along the x-axis.